We now move on to booth D, safety concepts for batteries. Benjamin, are you there?
I can hear you, yes.
Okay, if you could show us your slides.
Okay, are you guys able to see the screen?
That's it, thank you.
All right, perfect. Okay, then let me say something about the OBELICS use case cluster for the safety concept of the batteries. As Horst already mentioned in his introduction, that we have our own use case cluster for the safety and reliability of the batteries, and the cluster was mainly driven by the partners ABL, BOSCH, CEA, Fraunhofer, LBF, and the University of Zurich. So let me give a short introduction to the topic. So if we talk about safety and reliability, we have to separate between the electrical and mechanical domain. So both were addressed in OBELICS. So the cluster has three main use cases. Where number one, number two, dealing with the electrical safety. So here CA was developing an online electrochemical impedance estimation of single cells. And with this technique, the cell state of health can be estimated at any time. This is use case number one. Number two is led by the ABL, and they developed a new testing approach for the battery system where they can consider high switching frequencies up to 20 kilohertz. And with this testing concept, this testing concept is much closer to the field application and therefore relevant for the reliability testing. And on the mechanical side here, in the slide on the right, we're looking for the vibration response of the battery system and modeling approaches to predict these mechanical loads. And the mechanical use case is led by BOSCH and Fraunhofer LBF. And in the final step, the safety improvement of each proposal will be quantified by using a new probabilistic FMEA approach, which was created by the Fraunhofer LBF. So let's look at each use case. So number one here, I give you some details about it. And the purpose of this use case here is to address and explore the possibility to determine the state of a lithium-ion battery cell by using indirect measurements. And this goes with a general idea of a smart cell. That means a battery cell equipped with an embedded electronic system and optionally with some sensors which give it smart features as, for example, communication capabilities or even self-measurement. So more precisely, CA adapted the well-known electrochemical impedance spectroscopy into an embedded system, and the computation occurs on board of each cell. So this device was directly connected to a lithium-ion cell and tested at different temperature levels. And the results were a certain number of so-called Nyquist diagrams depicting the variations of the impedance of the cell. So, however, this is only half of the work. The second part of our approach was based on the development of a cell model calibrated on real tests that were performed on a lithium-ion cell. So a referent Nyquist diagram was obtained this way for each cell condition and in terms of the cell temperature and state of charge. And the final step is the exploitation of the results obtained in the two described ways. And we started from the assumption that with a quite satisfactory accuracy of the embedded electronic results, we can determine some points of the Nyquist diagram, what is showed here on the left. So these points have a direct correspondence to what was obtained from the embedded test and what is predicted by the theoretical model. So in a more practical description, as long as the difference stays below some predetermined thresholds, the cell can be assessed as safe. So the cell is leaving its normal and predictable state if a drift of some or all these meaningful points is detected. Consequently, the cell is entering a dangerous zone and could be close to a thermal runaway. So the major advantage of this technique is the improvement of the safety without complexing too much its hardware architecture. So this to the use case 1. Let's move to use case 2, which again was led by the LBL. So here the LBL was or implemented a 20 kilohertz battery testing approach, and these switching frequencies, as I said, occur on a vehicle level and should be also recreated during testing on a battery test bench. Current testing approaches provide much lower switching frequencies. Consequently, the gap between the test bench and the real world has to be closed. The work is split in 2 parts. So the first part is a new controller algorithm which was developed, and a new semiconductor technology with lithium carbide was implemented. Both parts will be used for a new power hill device for emulation of the electric vehicle components. The model predictive control (MPC) is presumably the most successful modern control technique. The technique makes use of a planned model and the measurement to calculate an optimal controller or control input, which minimizes penalty cost function over predefined prediction horizon, which is shown in the left picture. As for the power hill test devices, the lithium carbide technology is expected to design a more compact power system, consequently leading to further cost and weight reduction for the whole power system due to their advantage in higher switching frequencies and smaller jitter. About the in-vehicle application, they enable to design and fabricate inverters with significantly increased efficiency without the need for liquid cooling, and consequently saving the costs and extending the driving range. Smaller jitter of the silicon carbide MOSFET leads to less switching energy losses over the lithium IGBTs, as clearly illustrated in the right picture here. And let me come to the last use case about the mechanical safety. And here we focus on the vibration response behavior of the battery system in the vehicle and as well on the test bench. And there are different given standards to design the battery against mechanical vibration loads. But if you look at them, you will realize that there are quite big differences in the load assumptions. And therefore, this study was carried out to make a statement what standard can be used during a design phase of the battery system. So this slide shows a brief overview about the methodology we used for the study. And we started with our demonstration vehicle, which was already introduced by David, the vehicle Fiat 500e. So here we did an extensive study of global battery vibration response on a rough road track with different speed levels. So, but with this, or on this level, we were not able to apply sensors inside the battery system because of safety issues. So that's why we got a separate battery system, so a new one. Put it on a test bench, and with this one we were able to open it and also installed sensors inside this battery system. And now we were able to describe the vibration transfer path from the mounting positions of the battery system to internal components. And therefore the single battery system was tested on a multi-axial test rig at the Fraunhofer LBF with identical global excitations gained from the vehicle on the rough road track. So we basically tried to replicate the external loading based on the measurement from the real world or from the real vehicle. And here on the pictures you see this battery system on the test bench at the Fraunhofer LBF. And it was demonstrated that the vibration profile on the vehicle could be replicated on the test bench with a designed test frame and also optimized test rig parameters. So let me give you some results what we achieved. So here we see the vibration response on the battery mounting and on an internal sensor. And here we can conclude that the ISO 12445 standard gives a good approximation for the global response of the battery system. But if we look at the response of internal components and compare this to the ISO profile, then we see the ISO profile underestimates the loads, especially for higher speeds. So consequently, it can be recommended to not use the ISO profile for the validation of single battery components, because this can be non-conservative. So the transfer path for that has to be considered either by experiments or by simulations. And the final assessment to really calculate the improvement of safety, there is an approach by the Fraunhofer LBF. And here we use a new FMEA tool, which includes quantified failure probabilities. And this allows us to calculate the failure probability for a battery system with and without the new measures. And if the Fraunhofer LBF is in charge for that tool here. So that will be the end of my presentation, and I thank you for listening, and thank you all the partners for that great work.
Okay, thank you, Benjamin. We have a question here for you. In an FMEA, we've got another question. In an FMEA, you need to know the failure modes. How sensitive is the analysis of your approach to new failure modes in new chemistries or architectures we don't know yet?
Yeah, so that would be maybe a question for the Fraunhofer FBF. I don't know if somebody is online, but maybe I can try to answer it. So if you have a new, let's say if you have a new chemistry and then also different failure approaches or different failure mechanism can appear here, then this has to be implemented in the FMEA. So this is not automatically in there. So you still need to know your failure mechanisms for modified cell chemistry, and this has to be implemented in the FMEA. So this is it's not automatically in there for a new chemistry.
Okay, thank you. Okay, Benjamin, thank you very much for your presentation. We need to move on.